Hey, John here. Let's look and see how we can configure a bidirectional I/O pin so that we can use it in something like an I2C interface or a PS2 keyboard interface.
Big shout out to everybody that supports my channel and provides encouragement. I really appreciate it. Especially those VIP patrons listed here that have gone the extra mile. Thank you very much. Now, if you watch my channel, you've probably seen this before. If you've been following along the FPGA series, this is an abstract description of how the physical pins are connected to the FPGA. This is in the LP or the ICE40 LPHX family datasheet. There'll be a link below this video on YouTube to where you can find this manual. If you look at this, what you need to know is this pad here is what connects to a physical pin on the chip, okay? So this is how we interface to a single pin, a GPI, 1-bit GPIO type of I/O signal. You can pull it up if you want to under program control and you configure the FPGA. You can send data out to the pin through here. You can look at the value of the pin by monitoring this signal coming out over here. You can also use this to control this tri-state driver in here. And I talked about that in a video earlier in this series. There will be a link to the playlist that shows all kinds of FPGA stuff that this video is a part of below the video on YouTube, okay? So you can go back and see that if you want. The short of it is today, what we want to do is be able to send data out to the pin at some times and read it at other times. You might need to do this like in an I2C when you're providing, data pulses, and the device that you're talking to can also communicate back at you at the same time, because that protocol, like the PS2 keyboard and mouse protocol, or like the Dallas one wire and stuff like that, those things work with a pull-up resistor. And when you drive data out, what you do is you either drive it to ground or you let it float in what we would call an open collector driver, okay? Now, in order to do this with an FPGA, what you can do is you can just connect the output signal here to a 0, ground it. And then anytime this output enable is active, the driver goes on, and the driver will let the 0 flow out as ground out the pin. And if you put the pull-up on as well, assuming that the pull-up on the FPGA has the value you even want to use, then what would happen is when you're not driving this to 0, this pull-up resistor will pull it up to a 1. And usually that's part of how these things are intended to be used. The pull-up resistor on the ICE40 HX chips that I've been using, if you measure it with a voltage divider, it looks like it's 33K ohms, which is actually a pretty big resistance. For something like an I2C or something like that. Usually you'd want a couple of K in there, not a couple of tens of K. So while this could be useful for certain circuit designs and things, it may be that you're really going to have a physical one out here on the board anyway. I'm just saying, your mileage may vary. And because the input logic is always running in the FPGA, you can always take the signal that comes in over here and connect it to circuitry, whatever you want. So you can actually be outputting and inputting at the same time. All right? That's actually kind of cool. So here's a little test program I put together to demonstrate this. We have two different styles. I guess what we should do is first look at the PCF file. This is designed to run on a board that I designed a while ago. I'll put a link to this in the description below the video on YouTube as well, and the GitHub repo and all that with all the designs, schematics, everything else. So what happens is And all FPGAs that I've ever used have stuff like this is another point, right? So is this useful for more than just the ICE40? Absolutely it is. Pretty much all FPGAs have this kind of thing going on with their pins. And by that I mean this idea that you have an output enable and the output driver, and you can watch the input independently of what you're doing with the output. Some FPGAs have pull-ups and pull-downs, and all kinds of different variations. That's why different FPGAs exist. All right, so back to the PCF file here. What do we got here? Now, there's some games, because I'm using Yosys, and I mean, it does not have the most robust support for tri-state I/O in its implementation. So sometimes, if you want to get too fancy with it, you need to instantiate a hard macro, a hard module in your code in order to specify what features you really want in the pin configuration. Otherwise, it can infer it, all right? And what we're going to see today, it will be able to infer this fine. I've never seen this be a problem on other systems, such as the Xilinx, ISE, and Vivado, and so on. But Yosys does have a documented lack of robustness, I shall say, when it comes to bidirectional I/O, or more accurately, tri-state I/O. Okay, we talked about that before on this channel as well. Go back and look at the playlist of the previous video where I talk about the SBIO in great detail. Okay, so, and by that I mean the pull-ups don't always work, but the rest of it always does. I've never had any trouble with it at all. It's just whether or not the Yosys allows you to specify a pull-up when you're trying to get it to infer that you want it to implement a tri-state driver. Now, having said all that, let's look at some code. So what do we got here? We got two switches. Now, I don't even think I used this in this example code. So S1, when I press it, we will see that it will be tied to driver enable. In other words, when I press S1, because it's active low, driver enable will become true. And when I release S1, it will be false. And when the driver is on and off, that'll be controlling the output pin or the low impedance driver, right? When you release S1, it should float, and I'm going to have the pull-up resistor on. Therefore, this will basically reflect, when I press S1, it should definitely show a 0 coming out of the pin. And when I release it, it should look like a 1 as long as it's pulled up, okay? The LEDs are hooked up to the driver enable and the current pin value. And you'll see down here, I'm instantiating this block manually here. I commented out this define, so the if def is false. This is the inferred way to do it. This is the explicit way to do it. I talked about how you determine the pin type stuff last time. Link to the playlist below the video on YouTube. You can go find that, where I talk along about the SBIO stuff. I have the pull-up explicitly turned on, so even if you don't turn it on in the PCF file, it will be on because this thing takes precedence, and I take manual control there. The pin, the physical pin, is connected to D out, that signal there, which you can see is an in out. Okay, so that means that as far as Verilog is concerned, I can both read it and write it if I want to. Although I'm not going to directly interact with it because I'm only going to interact with it through this package pin of this other module here. But that's what's going on. That's what this means, I should say. Okay. For me to interact with it through this hard module, the hard IP here, I'm going to directly control the driver enable, and I can set a value on the output, and I can look at the input. The three items in the diagram we were just looking at are connected right here. Those three items being these guys right here, okay? The output enable, the output, and the input. And here down is the other bit in the configuration controls this pull-up. And the pin configuration has to do with telling all these muxes and stuff what they're supposed to do in order to connect it up so that the output just simply flows to the pad. The OE controls the driver, and the input flows through here, and I can just see it directly, okay? So that's all that's going on in this particular module. So in the end, what does it mean? I press S1, the driver goes on, and I output a 0. When I release S1, the enable is off. I don't output anything, but I can look at what's there, and I can take that pin value and I can see it on LED 2. And because there's a 1 here, I have the pull-up turned on. So it should look like S1 goes, high when I press it and low when I release it. If I just put a scope on the D out pin. So let's make sure it compiles right. Look for warnings, combo, that's just an FYI. No clocks, FYI, FYI, nothing interesting going awry here. Make prog. On my test board, we'll flash the ROM and we boot her up. All right, so I got my scope here on the D out pin, which is pin 143. This is S1 here. There's LEDs 1 and 2. LED 1 is off and LED 2 is on. LED 1 is off because I'm not pressing the S1 button. Therefore, the driver is not enabled and it is floating. And the LED says it looks like a 1 to me. And if we go over to our scope, it looks like a 1 to the scope as well. Now, if I press S1, you can see the LED. One of the LEDs goes off, the other one goes on. So LED number 1 over here on the end, the lowest one in the picture here, that's LED 1. So it's on because I have the button down. So that means the driver's on. LED 2 is off because I'm driving it to a 0. So that's what we should expect to see, and that's what the scope also says. Now if I release and press, it goes back and forth. That's what we would expect. Now I got a 33K ohm resistor right here, and I can connect it between the output pin and ground. And last time we noticed that if you do this when the pull-up resistor is on in the FPGA and the output is floating, then 33K ohms divides the output voltage in half. You can see that the LED turned off when I put that on there. I'll take it off here. The LED's on right now. I connect the pull down resistor and the LED goes off. If we look at the scope, we see that we're at about 1.6 volts, 1.6 something or other. That's about half of 3.3. That makes a lot of sense. If I press the button, we can see the driver's on and the scope says we're at ground. I release the button, it goes back up to the 1.6 some odd volts, and there we have it. This is definitely a pull-up output on the FPGA, and it's pulling it up 3.3K ohm. And I got a 3.3K on the outside, pulling it down, which is why we saw it divide by 2 on the scope. So that all makes perfect sense. Now, what else makes perfect sense is this LED going off, because we're at 1.6 volts is too low to look like a logic high. So the FPGA thought it was a 0. It was low enough to look like a 0. We can also just take the wire directly, and we can short it directly to ground, and of course it'll work fine. Definitely goes to 0 when you do that. So this is what would happen if you had a physical device connected up to this pin here that had an open collector driver on it when it wants to send data back to the FPGA. Either one of them can pull it low with a pull-up resistor somewhere, pulling it high when no one's pulling it low. This gives us the ability to have bidirectional communication on 1 bit of I/O with an open collector driver. Now, I don't normally like to do this, but we could go ahead and short it out and conflict it. So when I press the button, the driver is on right now and is driving it low. But we should be able to overdrive that by connecting this to 3.3 volts if we really want to. Temporarily, it shouldn't break the FPGA for a little second. And you can clearly see that the output goes high. So I'm looking at the output, the actual output pin, rather than what is supposed to be on the output pin on that LED right there. So this does verify that the circuit's doing what it's supposed to do. Don't short out your FPGAs as a general rule. It's probably not a good idea in the long term, because what you're really doing is you're driving, the maximum current out of it, and you really shouldn't do that. it could stress the driver or something like that and make it be weak or break it or something like that in the long run. Now let's look at what happens if we use the other code and you use the inferred tri-state driver. All right, so if you want to do that, you take this and go like so. And if we compile it, it'll compile these lines and ignore this. This is essentially commenting out this hard block here. Now, if the driver enable is true, we set D out equal to a 0. That's what happens here as well, right? If driver enable is false, we assign D out a high impedance. And that's exactly what this down here was doing, right? And we can also, this is how you can look at the input that may or may not be the same value that you assign up here, okay, in Verilog. So this should infer the same thing that's happening down here. And we can use our pull-up, pull-down resistor to figure out if that is what's going on or not. And we can do the same tests. Now remember, in the PCF file, I do have the pull-up turned on. We can turn it off like this if we want to, but if Yosis does the right thing, then there should be a pull-up on it. And I've done this before. I think it actually does do the right thing. Here's the usual warning that we get for tri-state logic. So, I mean, this is fully disclosed. It's not like it ain't great, it ain't wonderful, but they've disclosed it, which is critically important, so the world's not all confused. We got the usual warnings, blah, 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 no clocks. We know. Alrighty, make progit and test this one out. Again, when it first comes up after programming, we see the output is floating /high with a pull-up on it, or at least we so believe. The LED is on. We press this, it pulls the output low, and that LED goes off. The other one goes on because the output is enabled. Glancing over at the scope, I can see we have the same values, same behavior as we had before. Let's put on the pull-down resistor. And on the scope, we can definitely see it's pulled to half the voltage, which is exactly what it should be. If there's a pull down inside the FPGA, we can also see the LED is off. That means that the inferred logic is working correctly because this LED actually does show me the physical pin state as opposed to the value that's being driven to the pin, okay? If I turn it on and off like this, I can definitely see on the scope it goes to ground when the output enable is being driven. And when I release the pin, I can see the voltage goes up. In this case, with the pull-up resistor on there, it goes to 1.6 volts, as we would expect it to. I pull the pull down off, the LED goes on. So I'm definitely looking at the pin, what the pin has got on it. Now we can do the same game and do a little quick brief short out of the pin. Again, I don't recommend you do this very often, if at all. So without the external resistor, when I press this, the output will go to ground, and we can see the LED go on. That tells me the driver is on. If I overload the output and I pull it up to 3.3 volts, we can see the LED goes on like it should if the LED is watching the pin rather than the interior signal inside the FPGA that is driven through a buffer to the pin. So the inference that Yosis did there was absolutely perfect and correct. So you could do it either way on Yosis, and I happen to know on things like, the Xilinx ISE and Vivato and other tools, those will infer it correctly as well. So, in conclusion, we can infer a tri-state driver, like an open collector style driver with a pull-up resistor, and it works fine if we do this, and we can explicitly do it this way down here. Given that this can be tricky in Yosis and get weird at times, it may depend on whether I declare that as an output or an in-out or something like that, because it could flake out at me when I'm not noticing, and I do not want that to happen. I'm going to stick with this explicit style design here. That is, when I write applications for this particular board. I might actually go ahead and do this style when I write my applications, so that if somebody wants to port it to another FPGA, they definitely can without having any difficulty, because of the fact that this may only work on ICE40 family FPGAs. If you wanted to run it on an ECP5 or something else, this is probably not going to fly, unless they happen to use the same name for their modules with their hard IP silicon for other FPGAs, which is not a high probability, especially if you change brands. All right, so this, dabble around with it. Let me know in the comments below if you find anything else interesting or another way to do this. I think it's pretty simple. This is the standard Verilog way to make this happen. And like all FPGAs, the ICE40 has hard macros or hard module IP that you can use to explicitly configure the chip exactly how you want it to be if you so desire. So, that's that. Thanks for watching. I'll see you next time.